So could you please tell us about yourself?
Hi, so I am Durgesh Chandel. I am currently a postdoctoral associate at Massachusetts Institute of Technology. I am currently affiliated with Gas Turbine Lab, but also working with Hypersonics Research Lab. And my project is electric aircraft design and development.
So why did you want to become an aerospace engineer?
Aerospace engineering has been a branch of engineering which always fascinated me because this is one of the fastest mode of transportation, and also the engineering challenges we encounter in this field are unique. The safety margin is huge. We have like human lives on stake. So as scientists and researchers, we always have to make sure that things are super safe, and we work on cutting edge technological problems. And later on, the advancement we do in aerospace engineering, they can also be utilized in land-based applications such as automobile and other things. So it has been my dream to always work as an aerospace engineer.
Right. So can you describe and explain some of your work relating to hypersonic flight?
Yeah, so my PhD was in hypersonic aerothermodynamics. And at this point, maybe I can show a slide. So I'll just share my screen. Share a screen. Okay, it says host has disabled screen sharing.
Yeah, now you should be able to share it.
Okay, so during my PhD, I worked on the predicting aerothermodynamics behind the strong shock waves which are generated during the spacecraft atmospheric entry missions. So whenever we are launching these high-speed space exploration missions, rather like we are entering back, we are going to International Space Station or going to Mars. So we are basically entering at very high speeds with respect to the speed of sound in that atmosphere. And that leads to a strong compression of the air in front of the vehicle and leads to the formation of shock wave. And then behind the shock wave, because of the sudden compression, we have very strong heated zone where the atmospheric gases can reach to high temperatures such as 28,000 Kelvin, up to 28,000 Kelvin temperatures were seen for Orion entry mission. And similarly, when this gas interacts with the vehicle surface, it can lead to high temperatures as well. So for example, in this case, we saw about 2,500 Kelvin temperature. So at this high temperature, the heat, the base material can melt, and that's why we need the heat shield. And even the material has to be thermodynamically strong, means it should be able to withstand that temperature, but also it should be able to withstand that chemical environment. So what happens is during the high speed entry missions, the atmospheric gases have high enthalpy or the high total energy on the flow. So for example, here on the top right corner, I am telling typical range for the Earth entry speeds and flow enthalpy. And for example, we also have missions up to 60 megajoule per kg. And at this is very similar to like a explosion. So what happens, like the heat shield material gets melted, and it also gets eroded by the gases. The atmospheric gases, they are mainly made up of molecules, but once we have that high energy going into the flow, because of the sudden kinetic energy being converted into the gas internal energy, the different internal energy modes of the gas molecules get activated. So for example, the gas molecules, if you consider them like a dumbbell, they can like the most common mode of energy is the translation. So the whole thing starts just moving as a rigid system. That's the translational energy mode. But then the gas molecules can also vibrate or like rotate around an axis. So we have vibrational energy modes, rotational energy modes, which lead to the dissociation and ionization of gas molecules. So when the gas basically goes into a plasma state, and that plasma mixed gas mixture interacts with the surface of the aircraft or the heat shield, and then it can ablate that surface. So you really have to know the gas kinetics at that temperature, at what rate, like how many active species are there, what are their concentrations, etc. Because the main goal of this is to come up with optimal heat shield design. As we know that space missions are extremely expensive. So we want to minimize the weight as much as possible, but also for example, the heat shield has to be thick enough so that after the erosion, the hot temperature environment does not reach to the base metal. So yeah, during my PhD, that has been a focus of my research.
So what is the difference between equilibrium flow and non-equilibrium flow?
Okay, yeah, so that kind of follows up in the slide itself, and I answered it partially already. So what happens is when a gas has certain high energy, but all the energy is contained in translational energy mode and all the remaining modes, but somehow there is an equilibrium between these modes. So for example, there is energy exchange happening, but there is a steady state equilibrium which has reached. So then the gas state, for example, so gas thermodynamic state mainly consists of what is the pressure, temperature, and concentration of different species. So during the equilibrium, those things are kind of frozen. I mean, there are processes happening, but for example, a forward reaction is equally compensated by a backward chemical reaction. So then the net effect is as if nothing changes. So that's what happens in an equilibrium flow. And that is, the equilibrium is achieved when the gas molecules have enough time to collide with each other and exchange this thermodynamic information with each other. So basically during the molecular collision, there can be elastic or inelastic collisions, and there will be energy exchange. So then there will be energy distribution or redistribution between those two molecules. But if you are moving at a very high speed, which is the case in the hypersonic situations, the gas molecules do not have enough time to exchange this information. So what happens if there is one molecule which was just behind the shock and had extremely high temperature and energy in different modes, it cannot communicate with other lower energy molecules because the flow is that fast. They don't have enough time to communicate. So then what happens is it becomes a non-equilibrium gas mixture. And then there is a big gradient in, for example, static pressure, temperature, species concentration, etc. But finally, if you give the system enough time, everything will come to equilibrium. That's what happens if you have like a closed system. But for example, behind the spacecraft, let's say in the front, we have this shock wave formation, as I'm showing here in this picture. So just behind the shock wave, you will see strong non-equilibrium region because the shock has just formed, and the flow upstream to the shock does not have any information about it. But as you go further behind towards the rear of the space vehicle, then you will see that the gas starts to come in equilibrium as more and more molecules collide. The other thing is that at high altitude conditions, for example, when we are entering in the atmosphere of a planet, we are at very extremely high altitude and in a rarefied gas environment. So just because of the rarefication of the atmosphere, there are not enough molecules even for long distances behind the spacecraft. So here in this picture, we see this hot region trailing behind the spacecraft for a long distance. And that's the reason, because in this region, the equilibrium has not yet reached.
So How can this help or harm the flight of the aircraft or a spacecraft?
Yeah, so basically in engineering, we mostly prefer equilibrium conditions rather than the non-equilibrium, because predicting non-equilibrium is tricky. You need to know, because there are so many species, and then every molecule and atom has their certain vibrational and rotational energy levels. There are lots of energy excitation, exchange, and relaxation mechanisms happening all together. Then there are free electrons in the gases, so you have plasma. So then predicting all that is extremely difficult, but that happens in real scenarios like high speed atmospheric entry conditions. So but it's important to cover it because it harms the surface of the vehicle. Basically, if there is extremely high energy in the system and you do not know uh, the thermodynamic state of the gas, then you cannot design your system to be safe in those conditions. Um, so yeah, all I know is that non-equilibrium kind of harms the spacecraft, and even for hypersonic flight in atmospheric, like hypersonic aviation, for example, even there, having these strong shock waves and non-equilibrium phenomena can increase the turbulence in the flow and also can lead to instabilities. So flow instability. So again, leading to flutter and all those kind of problems. So it's not good, but it's like having non-equilibrium itself is not favorable. But if we can predict it accurately and model our system to withstand that, that's what is the goal.
So what are the benefits of developing hydrogen fuel powered for aircraft or spacecraft?
Okay, so yeah, that's my current project. So I have one slide on that too. So basically, right now there is a lot of interest using hydrogen as a fuel source because we are running out of fossil fuels, and also the emission restrictions are getting stronger and stronger. So then one of the projects which I'm working on is funded by NASA, and we are trying to come up with futuristic aircraft design. So we are putting a couple of new technologies together. For example, the aircraft is powered by cryogenic hydrogen fuel cells, and which run the superconducting motors. And finally, those motors drive the propulsive fans. So there is no internal combustion happening in this configuration. And then, so that gives us the power, but also we want to increase the aerodynamic efficiency of the system. So we use airframe integrated boundary layer ingesting propulsors. So as seen in some of these pictures, like these are some of the configurations we considered during the course of the project. So starting from left to right, on the left, we had a blended wing body configuration where the wing and the body are kind of like blended to increase the aerodynamic efficiency. And as you can see that the engines are placed behind on top of the wing, and it seems like that engines are also ingesting some of the boundary layer being developed on the wing. And then the tail is different too. There were a lot of considerations why we started with that. I will not go in too much detail, but some of the key highlights are that we are using distributed propulsion system, which also enables us to use electric motors as a source of power for the engines. Because if you go with conventional turbo machinery based fan design, and if you keep scaling them in order to achieve distributed propulsion, as the fan becomes smaller and smaller, you lose on efficiency. But with electric systems, you can still have high efficiency even with the smallest smallest fan designs. So yeah, we studied different configurations, and like right now, based on the system level optimization of different components and based on our requirements, what so we optimized on this particular design. So I should highlight that the main goal here is to come up with a sustainable civil aircraft design, because so far we have seen very many small aircraft, air taxis, eVTOL, SVTOL kind of concepts, and which have worked well. But the next leap will be to come up with a fully electric, small or large or mid-range transport aircraft. So then we can really reduce on carbon emission and fuel cost, etc. That will be true sustainable aviation.
Mhm. And can you give us an insight into some of the work that you've done both NASA and General Electric?
Yeah, so I will talk a little bit about what I did at NASA. I have just one more chart for that. Uh, okay, I'll share the screen again. So as I was telling before, when I was talking about my PhD work, that behind the shock, there are different regions. There is non-equilibrium region. And then as you go further, there are interactions between different shocks coming from different surfaces of the spacecraft. And then you can study these different regions for different purposes. For example, on the front is the highest temperature region, and you want to predict the non-equilibrium behavior. And then, so basically the way researchers solve this problem is by using three main things. One is like having a strong fundamental database to predict the chemistry. So using atomic and molecular spectrum data, energy transfer mechanisms, collision cross sections, radiative processes, etc. Then we do computational modeling and also measurements. So computational modeling is easier because you don't need a facility. So there are different techniques, and my work was mainly focused on computational fluid dynamic based designs. So I'll not go into much detail, but yeah, we used CFD solvers. Then finally on the measurement side, so we do need to validate our calculations based on some data. And then it's very expensive to do the flight experiments all the time. So um, uh, and then it also depends on at what level of modeling you are working on. So for example, the first thing will be to behind the shock, what are the different chemical processes happening? Like if, let's say, for example, molecular nitrogen is dissociating into atomic nitrogen, and then that atomic nitrogen is being converted into nitrogen ion and free electron. So then that's how you get the state of plasma mixture. So so this region behind this shock wave can be simulated in a shock tube facility. So at NASA Ames Research Center, they have a unique facility. It's called electric arc shock tube facility. So where they conduct high-speed shock tube experiments. So basically there are two big shock tubes, only one of them is functional. And then here you can have like a driver gas where you give a enormous amount of energy needed to generate high speed shock waves. And then there is a diaphragm between the driver gas and the driven gas section. So for example, let's say you want to test Orion entry conditions at Earth at 72 kilometer altitude. So you fill up your test gas section shown here in the gray with the air at those conditions. And then when the driver gas is heated with electric arc, so they are separated with the diaphragm. When the pressure is high enough, the diaphragm breaks. So the driver gas suddenly pushes this or compresses this test gas, and there is a formation of shock wave. And then we let this shock travel downstream. Here in this box, we see there is test section. So where you can make different measurements. So you can capture the spectroscopic image of the shock using high frequency cameras, and then you can backtrack on based on the spectrum intensity of different species. You can figure out the different chemical composition, etc. So that's how. So shock tube is mainly used. Shock tube data is used to validate the gas kinetic models and CFD models. So my job was to simulate this facility and provide complementary computations so that we can understand the test data better. And then at GE, I worked there for 3 years. It was in Bangalore in India. And I was mainly working on aircraft engine design. So first 2 years I worked on GE NX engine, GE 90 engine, compressor design, and FAA certification for the GE NX engine, where I designed the anti-icing circuit to make the aircraft safe during the icing condition. And for 1 year, I was working on combustion aerothermal design team. So where we were working on GE's new business jet aircraft engine. It was named Passport 20. So the requirements from a business jet are slightly different than from a commercial jet, because business jet aircraft usually fly at a higher altitude. So the cost is not an issue there, because the people who are flying there are rich enough, but then there are more restrictions on emission, because you are leaving those gaseous species at a higher altitude, so they stay there for longer. So yeah, those were some of the challenges I worked on.
So what would you say has been your toughest accomplishment so far?
In terms of toughest accomplishment, that keeps changing as as I've been growing. So yeah, I was born in a very small middle class family in India. My father's my grandparents and father and mom, they all came from farming background. So nobody knew about aerospace engineering. And so at that point, being an aerospace engineer was my dream, because I always used to look at a sky and look at the airplanes, wanted to design one. That time, I just wanted to get into the highest ranked college in India for for the aerospace engineering. So that happened. Then after that, I wanted to work for NASA. So when I actually got an opportunity to work on my PhD project funded by NASA, that was a good accomplishment. But yeah, as I said, you keep changing your next goal. So then after that, coming to MIT was the next step. And finally, when I achieved that, I was happy. And now I am looking forward to what's next in my career. I am also trying to apply for faculty positions, or do I want to work at NASA? So it's still in process. So we will see how it goes.
So what is a big milestone that you're looking forward to in your research?
Yeah, so my current research, as I mentioned, is on the fully electric transport aircraft. I'm really looking forward when they really enter into the service, because right now everything is at conceptual level stage. And different teams have been working on different portions or aspects of it. Like, for example, electric machine design for those conditions versus the airframe design versus the propulsor design. And there has been significant progress. So I'm really hoping to see some, large transport aircrafts, fully electric or powered by hydrogen fuel cell, coming to play. And then we can finally achieve our goals of zero emission, low noise, and sustainability in aviation, etc.
And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Yeah, so I will say starting early always helps. Because sometimes I see people are not clear on what they want to do, and that's perfectly all right. But as soon as you have realized your goal, then start working for it and start thinking about what are the skills required. Start connecting to people who are already in that field, and feel free to like ask for any help. And then later on, like once you, as you keep growing in that career too, like keep helping others as well who are behind you. So especially people in minority groups or coming from developing countries, because their aerospace engineering is not that mainstream. So I would really request them or suggest them to connect with each other and stay connected and help out. But in general, it's a very challenging field, so staying updated with the news and the industry demands, by news I mean the scientific news, what are the cutting edge challenges going on in the industry. So staying updated with the current research and innovation will always help.
Well, thank you for joining me, and thank you for letting me interview you. I think that was great.
Thank you so much. You started a great initiative. All the best.
Thank you. All right.
Thanks.